J-Land Bio here. Today we are going to finish up our gases unit by talking a little bit about gas stoichiometry. And you thought you got rid of stoichiometry. You thought you were done with that. Well, I'm here to tell you it is back. And it is going to be intense because we are going to be combining some of the key factors of utilizing stoichiometry with some of the gas laws that we have been talking about. It's going to be exciting. It's going to be fun. But it's going to be a bit challenging, so follow along very closely, and we'll make sure that we review this when we come back to class next time. A little bit about our learning targets for this particular video. You should be able to understand the relationship between volume and moles of a gas. You should also be able to explain the concept of standard temperature and pressure, and also be able to perform stoichiometric calculations based on the concepts of the ideal gas law. A couple of key vocabulary terms that we need to make sure we understand. The first is standard temperature and pressure, also known as STP. Then we'll also be discussing the molar volume of a gas. So think way back to our stoichiometry unit in January. We know that the coefficients of a balanced chemical equation represent the mole ratios in the equation. So if you look on the right here, we've got a equation that represents the Haber process, being able to create ammonia. 3 moles of hydrogen plus 1 mole of nitrogen will give you 2 moles of ammonia. Well, with gases, these can also represent volume ratios at standard temperature and pressure. Standard temperature and pressure is always 0 degrees Celsius and 1 atm, or if you're in Kelvin, 273.15 Kelvin and 1 atm. So at that particular temperature and pressure, the mole ratios also represent volumes, meaning that I can combine 3 liters of hydrogen with 1 liter of nitrogen and produce 2 liters of ammonia gas. So what's important to understand here is that at STP, there's a relationship between the moles of the gas and its volume. And that ratio is that 1 mole of gas is equal to 22.4 liters. Now this can be used as a conversion factor between liters and moles. And we're going to utilize that here in some practice problems. Now, when we expand on this a little bit more, gas stoichiometry can be a bit tricky. You need to really be close and identify what is given and what we can solve for. So for some instances, you can use the conversion factor between volumes and moles, and sometimes you'll need to use the ideal gas law. It's just going to depend on what's given to you in the problem and how you go about solving it. But there will almost always be 2 components of a gas stoichiometry problem. There will be a stoichiometry part where you'll need to convert from one chemical to another, just like what we did in the stoichiometry unit. There will be another part of it where you'll probably need to use the ideal gas law. So you can see here there's a lot of different steps, directions that we can go here. But I think what you'll find is that if we identify what we have and what we don't have, it's going to make life a whole lot easier, and we'll be able to figure these out. Now these are some of the most complex problems that you are probably going to experience in the gas unit and really in all of chemistry. But if you follow each step closely, you read the directions, you should have no problem. All right, we got 3 practice problems we're going to go through today. Let's get going. Our first question states, what volume does 0.0645 moles of gas occupy at STP? So let's take a look at what's given to us in the problem. We've got 0.0645 moles of gas, and it is at STP. The question is asking for volume. Now this is pretty easy. We know our number of moles, and we know it's at STP. So we can use the ratio that we talked about before, where 1 mole of any gas is equal to 22.4 liters. So this becomes a simple dimensional analysis problem. We start with 0.0645 moles. Moles goes on the bottom of the next step, and there's a direct conversion between moles and liters. 1 mole is equal to 22.4 liters. We plug those numbers into our calculator and solve. Pretty straightforward. So what we end up with is, with correct significant figures, there should be 3, 1.44 liters of our gas. Now, that's an easy problem. It's going to get a bit more complicated, but what you want to look for is, are we going from moles to volume, and is the gas at STP? If it is, you can use your 1 mole equals 22.4 liters. Let's look at a little bit more challenging type of problem. What volume of NO2 is produced from the combustion of 100 grams of NH3, assuming the reaction takes place at standard temperature and pressure? All right, so let's take a look at this problem as well. The question is given us 100 grams of NH3 is telling us it takes place at standard temperature and pressure, but we're asking for the volume of NO2. So we're not given moles. Remember, if we're given moles and we're solving for volume and it's at STP, we can use 22.4 liters. But the issue here is we're given grams of NH3, and the question is asking for volume of NO2. So this is where the stoichiometry comes into play here. I'm going to convert grams of NH3 into moles of NO2. And then I'll use the previous equation, 1 mole equals 22.4 liters, and solve for the volume of NO2. So let's go from here. We're going to start with 100 grams of NH3. Grams of NH3 on the bottom of the next step. And we want to convert that to moles of NH3. We check our molar mass for that, and that's going to be 17.04. Again, moles of NH3 on the bottom of the next step. And what we want to get this into is moles of NO2. We always want to get it into what the question is asking for. So check out our mole ratio, 4 to 4. All right. And now we should be able to solve this. So what that gives us is 5.87 moles of NO2. Now that we have our moles of NO2, we can then use 1 mole equals 22.4 liters. Since we're at STP, we have moles, and we're looking for volume. So we're going to take 5.87 moles of NO2. We're going to go from moles to liters, and 1 mole is 22.4 liters. So when we do this, we're going to get our final answer. Using 3 significant figures, what we end up with is 131 liters of NO2. All right? So it is a bit of a two-step equation, but again, look at what is given to you in the problem, look at where you're going to go, okay? And then devise a plan. In this case, we're going to do our stoichiometry first, and then we're going to use our gas values to be able to solve for liters of NO2. Let's do one more practice problem. All right, let's take a look at this last problem here. How many liters of NH3 can be produced at a temperature of 27 degrees Celsius and a pressure of 760 torr if 20 moles of N2 are consumed? So we got a lot of information here. So let's break this down. We have a temperature of 27 degrees Celsius, a pressure of 760. And we also have 20 moles of N2 that are consumed. The question is asking for liters of NH3. So here's always, I think, a good rule of thumb for this, is if the question is asking for something using the ideal gas law, you're going to use the ideal gas law last. In this instance, it's asking for liters. That is the last step that we are going to perform. What we are given to start with is 20 moles of N2. So what we need to do is convert that to moles of NH3. Here's another way to look at this as well. For N2, we're given 20 moles. For NH3, we're given a temperature, a pressure. The question is asking for volume, and we don't know moles. But we have moles of N2. So we can use stoichiometry to convert between moles of N2 and moles of NH3. Then we can plug that in and solve for liters of NH3 using PV equals nRT. So let's start this problem. We're going to start with 20 moles of N2. This is nice because this is just a simple mole to mole. Use the coefficients of the equation. So what we get is 40 moles of N2. The next step we're going to do is we're going to use that in this equation to solve for PV equals nRT. Now, a couple things here. Our pressure is given in torr, so we're going to need to convert that to ATM. And our temperature is in Celsius, so we need to convert that to Kelvin. Now, we should already be pretty well aware of how to do that. There's 760 torr per 1 atmosphere, so if you do the dimensional analysis, you're going to find that we have 1 ATM. And 27 degrees Kelvin is going to end up being 300.15 Kelvin. So we can plug those into PV equals nRT and solve for our volume. So P, pressure, 1 ATM, volume, which is unknown, equals N, 40, R, 0.0821, and T, temperature, 300.15. And now we can algebraically solve for x. What we get is 986 liters. Okay? Well, of NH3. Don't forget to put that down. Jolene made a mistake. Let's make mistake the word of the video. Okay? Mistake. Because I make them every once in a while. Not perfect. Close, but not perfect. So, mistake is the word of this video. So as you can see here, we'll do some more practice problems with this. This is a bit complex, but again, look at what's given. Look at where you need to go. Think about where you should start, because you're going to have to do some part of stoichiometry, some part of gas law in all of these equations. So long story short, keep in mind that there's 22.4 liters in a mole of gas if the gas is at STP. So keep that in mind. That makes some of these conversions a lot easier. You don't have to go through all the gas stoichiometry if you know your gas is at STP. And gas stoichiometry problems may involve using the ideal gas law and dimensional analysis problem, particularly with stoichiometry. So odds are you're going to have to use some combination of those two. Take a look at what you're trying to solve for, and then usually you end up starting with the opposite thing. So hopefully you understand your learning targets for this video. Bit of a long one, but lots of things going on with gas stoichiometry. So we'll see you next time. This is the last gas video, and we are going to move on to solutions coming up shortly. Have a great day, guys. We'll talk to you later. Bye-bye.